Hi, my name is Michael McMahon. I'm a member of the core libraries team in the Java platform group at Oracle. And I'm going to be talking today about the networking enhancements since JDK 11. So the presentation consists of two parts. The first part is an overview of the major work on networking since JDK 11. It covers NIO, so the java.nio.channels package, and classic networking, so everything under java.net. So the format then is going to be a list of items per JDK release with a brief description of each item. Some of these items may have been backported to other releases, but I'm going to introduce them as part of the release that they were originally developed with. So then the second part of the talk is going to be a review of some of the features that I identified above, just a small number of the more important ones. And they'll be identified in the first list with an asterisk. So first, to go with the most recent release, JDK 19, the first feature I want to talk about is HTTPS channel binding support for Java, GSS, and Kerberos. So channel binding, it's a technique to mitigate against certain kinds of socially engineered man-in-the-middle attacks. So what can happen in this type of attack is that a client may be induced to connect to an attacker's site instead of the server or a site that it was intending to connect to. And the client may think that it has a normal TLS session to the server, but it has a TLS session, but to the attacker site instead. And the attacker then opens a TLS session to the real server. So that the man in the middle then, or the attacker, is able to relay authentication requests from the server back to the client, and then the corresponding credentials from the client back to the server. So what the attacker can end up with then is a fully authenticated session that it has control over. Now, it might not have access to the username or password, but it can do a lot of damage, obviously, with full access to an authenticated session. So how does channel binding help with this? Well, it makes use of a property of TLS, in this case, the server certificate, and in particular a hash of the server certificate. So you can see in the top line of the diagram, it's a normal connection from a client to a server. What happens is the client extracts the hash of the server certificate after it opens the TLS connection, and it creates a channel binding token as a hash of that server certificate, passes that up to the authentication protocol at the layer above. In this case, it's Kerberos. And the channel binding token is combined with the existing user credentials that are used in the protocol. So this is all passed over to the server, and the server is able to verify that the channel binding token that it receives corresponds to its own server certificate that it provided to the client. So what happens then in a case where an attacker gets in between? Well, in this case, the client has, instead of receiving the server certificate, has actually received the certificate from the man in the middle. So this is denoted as cert M in the diagram as opposed to cert S. So the client doesn't know this, but it derives the channel binding token from cert M instead of cert S, and that's passed up to the Kerberos layer. So the channel binding token is then passed over to the server, so the server is able to see that the token is wrong in this case because it's not derived from its own certificate. So the server it sees a red flag, it's able to disconnect the session before any damage is done. So this is a useful technique that doesn't require any API change. So it's controlled in JDK 19 by the use of a system property. So you can, if you check the release notes, you'll be able to see how to use that. And because there's no API change, this feature has been backported to a number of different releases. Okay, so second feature then, MD5 and SHA-1 are disabled by default for HTTP digest authentication. So this is just a simple, it's part of a general effort to make sure that the JDK platform doesn't use crypto algorithms that are unsafe or insecure, as MD5 and SHA-1 are. So previously, if a server proposed the use of MD5 or SHA-1, we would have just said, yeah, okay, they're not preferred, but we will use them. But now, since JDK 19, such requests will be rejected with an IO exception by default. Now, if it's the case that the user still needs to use these, has no alternative but to use these algorithms, then there is a way of opting in and overriding that behavior and restoring the pre-JDK 19 behavior. So thirdly, we've improved HTTP proxy detection on Windows. So proxy detection is tightly integrated with the proxy configuration on the Windows operating system. And that comprises multiple different ways of configuring proxies. So previously, we would cycle through the available proxy configuration options and just take the first one that was returned. And if that one worked, then fine. If it didn't work, then proxy detection failed. So instead, what we do now is we cycle through the list, and we don't stop until we find one that does work. So this makes proxy detection more reliable on Windows now. So fourthly, we've made an enhancement to HTTP URL connection such that the default keep alive timeout is configurable. So normally the keep alive timeout is specified by the server in one of its response headers, but if the server doesn't specify the keep alive time, then previously a hard-coded default was used. So now this is configurable through two system properties, one for servers and one for proxies. So you can set whatever default keep alive time you wish. So now just to go on to JDK 18. First feature in JDK 18 is JEP 408, the simple web server. So I'm going to talk about that in more detail in the second part of the talk. But just to summarize, this is a simple command line utility which implements a simple HTTP-only static file web server. It's intended for educational or testing use primarily, but it also provides an API which can be used to customize it. So for example, to make it use HTTPS instead of HTTP. I'll talk about that a little bit later. The second feature then is the InetAddress Resolution Service Provider interface. As you probably know, InetAddress is used for lookups of DNS or host names, hostname to IP address and IP address to hostname lookups. What this service provider provides is a way of configuring alternative implementations of that lookup mechanism. And I'm going to talk about that in the second part of the talk as well. Thirdly, we've removed support for pre-JDK 1.4 datagram socket implementations. So this doesn't affect user code. It only affects implementations of datagram socket impl other than the one provided in the platform. And even then, it only affects or potentially affects implementations that haven't been compiled since JDK 1.4. So that seems kind of unlikely that that too many such implementations exist or will be affected by the removal of this runtime support. We've also removed the legacy plain socket impl and plain datagram socket impl implementations. These came in a number of releases back in JDK 13 as part of JEP 353, where we provided an alternative implementation of the native code elements of socket and server socket based on the NIO native code. I'll talk about that later on as well. But as part of that work, we provided a system property that allowed you to reinstate the old implementation if there were unanticipated compatibility issues that we hadn't anticipated. But since then, we have found that there hasn't really been any major issues, so it seems safe to remove the old implementations because they're no longer needed. So to go on to JDK 17, datagram socket can be used directly to join multicast groups. This is to work around a problem in the multicast socket class where it was difficult to override the implementation of multicast socket. So what we've done here is we've added the capability to join multicast groups to datagram socket in a similar way to how it was done with datagram channel in NIO. So now it's possible to do both unicast and multicast UDP using datagram socket as it is with datagram channel. So therefore, the multicast socket class can be deprecated. We've also deprecated the socket implementation factory mechanism. This was a JVM-wide, a couple of methods on socket and server socket that sets a JVM-wide factory mechanism for socket impulse. So a preferred way to do that now would be to subclass socket or server socket and pass the desired socket impulse through the relevant constructors of socket and server socket, and that could be done on a per socket basis rather than setting this factory that affects the socket impulse for every socket and server socket on the entire JVM. We also provided in JDK 17 a new implementation of selectors for Microsoft Windows. So this implementation is based on the WePol library, which sits on top of the auxiliary function driver in WinSock. So this is a big improvement on the existing selector mechanism for Windows, which was based on the old select system call. That old system call is not particularly scalable because it uses arrays of file descriptors or socket descriptors. There's a lot of data to be copied in and out on each call, and also there's a limit on the number of sockets that can be handled in an individual select call. So the limit was actually 1024. So servers that needed to handle more than 1024 sockets had to have a dedicated thread in the selector for every 1024 sockets. So all of that is gone now. This new implementation is it's similar to the EPOL, similar architecturally to the EPOL driver in Linux, and is a lot more efficient and performant than the old one. So JDK 16 next. The first one here is JEP 380, Unix domain socket channels. Again, I'm going to talk about that one in the second part of the talk. But just to summarize, Unix domain socket channels are used for local IPC, so local interprocess communication between processes on the same system. So that allows you to bypass the TCP IP stack, which leads to better performance and potentially some security improvements as well, which I'll mention later. HTTP client implementation returns cancelable futures. So this is the HTTP client that was introduced in JDK 11. It's an asynchronous API built around the completable future class. So completable futures are cancelable. So if you call the cancel method, that works fine, but it's only partially implemented prior to JDK 16. So since JDK 16, the cancellation works all the way down through the protocol stack. So for HTTP 1, that ends up with the TCP connection being closed. For HTTP 2, the relevant stream gets reset. So that works exactly as you'd expect. So going back further, JDK 14 and 15, we added support for a Linux-specific socket option called SO incoming and API ID. This is used for certain kinds of highly scaled servers that are handling multiple large numbers of incoming streams of messages. So it allows the server to query a unique ID associated with each incoming stream, which allows them to be streams to be grouped together in smaller numbers of threads. And this is a big efficiency gain on Linux. We also removed the terminally deprecated Solaris-specific socket option called SO Flow SLA. This happened at the same time as the Solaris port was removed from the platform. So there were a small number of Solaris-specific APIs that had to be removed at the same time. JDK 13. So this was similar to the what I mentioned earlier about datagram socket impls prior to JDK 1.4. In this case for socket impl rather than datagram socket impl. These implementations are no longer supported at runtime, but we haven't seen any compatibility issues. It's highly unlikely that many of these implementations still exist, as they haven't been compiled since JDK 1.4. And then the major innovation in JDK 13 was the re-implementation of the legacy socket API that I mentioned earlier. This was done primarily as part of Project Loom. So it replaced the existing native code associated with legacy socket and server socket and replaced it with the equivalent from NIO, which is based on non-blocking implementation. So this allows the legacy blocking APIs to work to play well with virtual threads, basically. So as part of that work, because a lot of native code is being replaced, we provided the ability to reinstate the old implementation if anyone ran into compatibility issues. But we haven't seen any significant compatibility issues. So as I mentioned before, in JDK 18, the ability to use the legacy implementation has since been removed. And just for reference, I'm not going to talk about it, but JDK 11 was the release where we introduced the JEP 3.2.1, the new HTTP client API, with support for HTTP 2 as well as HTTP 1.1. Okay, so now I'm going to just go quickly over a small number of those features that I just mentioned. The first one is the simple web server introduced in JEP 4.08. This comprises two things: the J web server command line utility, which out of the box it acts as a simple static file server, does HTTP only, and is intended for test or educational use primarily. But we also provide an API which allows you to build more advanced use cases, such as configuring the web server to use HTTPS instead of HTTP. So to take a look at the command line itself, if you type jwebserver-help, this is what you'll see. So I'll just briefly go through the options that you can supply. -B is an address that the socket will bind to, or an address that it'll bind to. By default, this is the loopback address. So the more common use case probably would be to use -B 0.0.0.0 or -B : which is the IPv6 equivalent. -D then specifies the root directory that's going to be served, where the content is going to be served from. -O is used to specify a logging level. So the logging level can be either none, info, or verbose, and the default is info. -P specifies a port that you can listen on. And I think -H and -version are kind of self-explanatory. So let's take a quick look at the API that can be used to customize the server. This is defined in a simple file server class in ComSunNet HTTP server. It defines three new types: there's an enumeration called output level, which is equivalent to the 3 logging levels that I mentioned earlier. The second is a method called create file server, which returns a configured HTTP server. And probably the more useful one is create file handler, which returns an HTTP handler, which can then be combined with other handlers in a way I'll show in the next slide, so that you can create more sophisticated servers that use the simple file server, but then do other maybe dynamic responses to other types of HTTP request. So the class that allows you to build, to compose multiple HTTP handlers together, you can use this HTTP handlers class. It has 2 methods. One, the first one of, which returns a handler which returns a fixed response to whatever incoming request that it receives. So the response that it returns is specified by the 3 parameters to the method: the status code, the response headers, and the string body. But the more interesting method here is the handler else, which I'll show a demonstration of in the next slide. It takes 3 parameters. The first is a predicate on the incoming request, which, depending on whether this returns true or false, either of the second or third HTTP handler is selected and used for that specific request. So before we go on to the next slide, just to introduce the request interface. This is a new interface which just provides a read-only view of the incoming request. And these are essentially the parameters that the predicate can look at and decide, can use the request URI, the request method, or the request headers to decide which handler to pass the request onto. So here's an example of this being used. It's an HTTP handler which combines a custom put handler with the static simple file server. So you can see what's highlighted at the moment is the predicate. So the predicate takes a request and returns true if the request method is put. So if request method is put, then the second parameter, which is this HTTP handler, is invoked. So this is the custom code that would be used to handle the put request. And if the request is not a put request, then it's passed to this handler instead, which is the static file handler. We're kind of assuming here that it's probably a get or a head request of some sort, which is what the simple file server handles. But you can combine these handlers arbitrarily and make them as complicated or as simple as you like. So to go on to the next feature, the InetAddress Resolution Service Provider interface, just to recap that this provides the implementation of the JavaNet InetAddress class, which is used to map DNS names to and from IP addresses. So an example of a forward lookup, if you call InetAddress.getByName on a host name, what you get back then is an InetAddress object, which includes the original host name and the IP address that corresponds to it. Then we have a reverse lookup example, which takes the address that was returned, in this case, the address that was returned in the first example, and hopefully it should return the original host name that you passed in. So what does this service provider interface actually look like? So this, we're looking at it here. It's implemented by the service loader class. So service loader is used to locate, first of all, an InetAddress resolver provider. You can see there, InetAddress Resolver Provider is an abstract class which contains a sealed interface called configuration. And one of these configuration objects is passed to the resolver provider to help it set up and return the InetAddress resolver itself. So the configuration includes a reference to the built-in resolver. So that means that the alternative InetAddress resolvers, they don't have to completely replace the built-in resolver. They can enhance it in some way And then the configuration also returns a reference to the local host name. So the main method in InetAddress Resolver provider that gets invoked is the get method, which is supplied with a configuration object, and it is expected to return an InetAddress Resolver, which is the actual service provider interface itself. So InetAddress Resolver comprises two methods, as you would expect, one to do forward lookups and one to do reverse lookups. Lookup by name is the forward lookup. It takes a string host name and a lookup policy object. So lookup policy object, or the lookup policy class, is an encapsulation of the bitmask values that you can see at the bottom of the screen there. It allows you to select whether you want IPv4 and or IPv6 addresses returned, and depending on which of those, you can choose to select either IPv4 or IPv6 addresses to be returned first in the list. So that essentially encapsulates in the service provider interface what InetAddress needs from an implementation, an underlying implementation of InetAddress Resolver. Okay. So the last feature I want to talk about is JEP 380, the Unix domain sockets. So as I mentioned before, these are used for local IPC with the server socket channel and socket channel classes. So in this case, local sockets are addressed by file system path names. So rather than IP address and port number, as in the case with TCP/IP. So an example file system path name is given there, /temp/foo.sock. Or any type of path name. So we had to define a new socket address type to encapsulate that type of address, and that's called java.net.unix domain socket address. And that is the main difference, the main addition to the API that captures the difference between Unix domain sockets and existing TCP/IP sockets. Now, the second difference would be in the area of socket options. Obviously, Unix domain sockets don't support TCP socket options and vice versa. But Unix domain sockets have one or two socket options of their own, such as the one identified here, SO peer cred, which is an option you can get on a connected socket channel, and this returns the user and group ID of the connected peer. So obviously there's no equivalent to that in TCP sockets. But apart from those two differences, socket channels and server socket channels should behave exactly the same with Unix domain sockets as with TCP sockets, except they should be a bit faster, possibly up to 20% faster with Unix domain as compared to TCP. Lastly, the system inherited channel mechanism, which is a kind of a bootstrapping mechanism for kicking off a JVM. This mechanism also supports Unix domain sockets, so long as the underlying launching framework supports them too. So we'll take a quick look. Oh, before that, just a comparison of TCP sockets, loopback TCP with Unix domain sockets. On the left-hand side there, you can see two sockets loopback, but they go through the full TCP/IP stack and the loopback interface, whereas on the right-hand side, Unix domain sockets can bypass all of that with corresponding improvements in efficiency and performance. So just a quick look at the API itself and how it's used. This is an overview of the Unix domain socket address class itself. It extends socket address just like INET socket address does. It has a single instance method called getPath, and that returns the path corresponding to the address. These address objects are created, and they can be created by one of two factory creation methods, one that takes a string path name and the other takes a path. So it's a very simple class. So how do you create these? We'll take a server first. So this is how you would typically create a Unix domain server socket. You would call server socket channel.open, and supply the standard protocol family.unix parameter. So you have to specify, for server sockets, you have to specify the standard protocol family.unix. Any other way of creating server socket channels will default back to the old TCP/IP sockets. So typically then you would call server.bind and give it a Unix domain socket address, such as the one created there, /temp/foo.socket. Now you can create client sockets in exactly the same way, but using the socket channel class instead of server socket channel. So they can be bound to specific addresses if they need to be bound. But like TCP, it's not necessary to bind client sockets in this case. And a simpler way to create a client socket is to use the existing socket channel.open method, which takes a socket address. So in this case, if the socket address is a Unix domain socket address, it will create a Unix domain socket and connect it to the destination address that you have supplied. So one other interesting use case with Unix domain sockets concerns containers and shared volumes. So this illustration here shows how you can, let's say you have two containers, container 1 and container 2, and you have a shared volume that's visible to both containers. So container 1 could bind a socket to a path name such as /vol1/socket in the shared volume, and then the second container can connect to the server through that name in the file system. So this is a kind of a useful ability to allow for inter-container communication. Sometimes that can be slightly more difficult to set up using TCP/IP sockets than as shown here. So just to recap, what we've done is we've looked at some of the work that we've done on networking since JDK 11. I've only talked about a subset. There are many other bug fixes that have been done since JDK 11. I also gave a little more detailed look at the simple web server, the InetAddress Resolution SPI, and Unix domain sockets. There's a link there to a more detailed article on inside.java, which gives more interesting or even more about Unix domain sockets that you might need to know if you want to use them. For more information, go back to the JDK release notes. Each of these items has more information, including links to the original bug reports, probably with more information. If you have questions or feedback, email netdev@openjdk.org. And that's it. Thank you for listening.